All right, in this video, we're going to discuss the idea of the tangent plane as it relates to multivariable functions. If this is helpful to you at all, please leave a like. Let's get into it. All right, so in Calculus 1, we learned how to find the tangent line of a single variable function. All right, so we got two axes here. So we got x and we have f of x, right? And we have some function. We pick a point along this curve and we draw a line so that it just barely touches the function at that point. That is the tangent line. All right. Now, we can move this point somewhere else and the tangent line will change. There's a function that will give us the tangent line at any point along f of x, and that function is the derivative of f of x with respect to x, right? So df dx. Now, this works for just these two-dimensional functions, but what if we take it all the way to some three-dimensional multivariable function? What does that even look like? So instead of having a tangent line, we have a tangent plane. And what that tangent plane is just like that line barely touched the surface of the two-dimensional graph. This plane is barely going to touch the surface of this three-dimensional object, right? So right here we have a paraboloid, and we're going to pick a point, P, and let's go ahead and sketch what this tangent plane might look like. Right? This plane barely touches the surface, and only at P. It doesn't touch anywhere else. What do we need to actually define what this plane is? So in a previous video, we covered what you need to define the equation of a plane in 3D space. You need a point on the plane, and you need a normal vector for that plane. Now, what is a normal vector? Well, basically, a normal vector is just a vector that is perpendicular to the plane, right? So no matter which way I turn this plane, that vector will always be perpendicular to the plane. All right, so let's recall what the plane equation is. From our previous video, we have that the equation of her plane in 3D needs two components, a normal vector and a point on the plane. Right? We called it P naught. So let's go ahead and label this as P naught. And the normal vector we called N. And the point has three components, x naught, y naught, and z naught, and N has three components, a, b, and c. And then from those components, we get this equation. If you'd like to learn this in further detail, go check out my video on the equation of a plane in 3D. Now, let's get to an example problem that asks us to find the tangent plane of some multivariable function. Okay, in this problem, we're given f of xyz is some function. Find the tangent plane equation and the normal line equation at f of 10, 6, 6. So what does this mean? This is the point that we're looking for the tangent plane at. So we can already know, right, what P naught is. P naught is equal to 10, 6, 6. And to find the plane equation, the only other thing that we need is n, the normal vector. And what is that equal to? Well, we're not given that. So we're going to have to figure out how to evaluate that. Now, it turns out that the normal vector for a function of three variables, right, at least in three-dimensional space, is the gradient, right? So if we find the gradient function, which we figured out in a previous video that we did on gradient functions, the gradient of f, x, y, z is equal to, uh, let's see, it's equal to a vector, right? It spits out a vector that is partial derivative of f with respect to x, partial derivative with respect to partial derivative of f with respect to y. And the last component, I'm pretty sure you can guess, is going to be the partial derivative of f with respect to z. Okay, so let's go ahead and each of these partial derivatives are going to be evaluated for whatever value you plug inside of x, y, or z. So let's go ahead and work through what this would look like. So first we need to find these different partial derivatives. So now we can throw all of these back in our vectors and we can say that the gradient function is equal to 4x minus 36, 2y minus 16, and 2z minus 8. And this function is going to give us our normal vector, right? Okay, so let's plug our values in for x, y, and z and see what we get for our normal vector. So our value for x is 10. So it would be for our first value. So let's go ahead and f of 10, 6, 6, right? Gradient function of 10, 6, 6 is going to be 40 minus 36, right? Which is just 4. Then 2 times 6 is 12 minus 16. It's just negative 4. And then we have 2 times 6 minus 8, which is just positive 4. And that is going to be our normal vector. I apologize, I made a mistake in my partial derivatives up here. This is actually minus 8, which will make this not a negative 4. This will be a positive 4. Okay, just to review what we did here for the normal vector, we took the gradient function of f of x, y, z, right? Which was which is a vector composed of the partial derivatives of each of the components, right? Partial derivative of f with respect to x, partial derivative of f with respect to y is our y component, and then partial derivative of f with respect to z is our z component of our vector. We found each of those partial derivatives. Then we built our function based off of that, and then we plugged in the point at which we're evaluating for the normal vector into that when we got out this vector. Okay, so let's take this and bring it up top here. So normal vector is 4, 4, 4. Great. And then get rid of all this. Let's go back to our problem. Okay, so find the plane, the tangent plane equation. So we have the normal vector and the point. So we can go ahead and write that equation. Now, how is that equation structured? Well, let's go back here and we'll steal this and bring it over here. And we'll go ahead and write it as such. So we have 4 times x minus 10 plus 4 times y minus 6 plus 4 times z minus 6 is equal to 0. That's our tangent plane equation, but can this be simplified? Yes, it can, because we have 0 on the other side. All of these can just be, all of these 4's can just be divided out. So we end up with x minus 10 plus y minus 6 plus z minus 6 equals 0. And if we bring all of these constants over to the other side, then we have x plus y plus z is equal to 22? Yeah, 22. All right. So everything simplified. We have our normal plane equation, or sorry, our tangent plane equation. Great. Now, the only other thing that it asks for here is our normal line equation. Now, what do we need to make a line in 3D space? Well, we also covered this in the previous video, but basically, you just need a point and you need a vector. Now, it's not this point and this vector, it's this point and, well, actually, no, it would be. It'd be this point and the normal vector. Because the normal vector is along the normal line. Now, let's look at what the normal line is. What are they asking for here? The normal line is this line right here. It goes all the way through, off in whatever directions, all the way through that point in that vector. So we already have a point on the normal line, and we have the normal vector. So let's go ahead and write our equation, or a system of equations, for the normal line. So if you recall, for a line in 3D space, most of the time it's not actually going to be one equation. It's going to be a system of equations, right? It's going to be an equation for an individual equation for each component of the point that comes out of the line. So for an x, y, z, right, point that's going to be on this line, you have x of t, y of t, and z of t. These are all just your functions for the points along the line. So if you recall from the previous video, we have that the x of t is going to end up being 4 times t plus 10, and 4 times t plus 6, and 4 times t plus 6 for z. All right. And if we wanted to write this in sort of a vector form, we could do, I don't know, L of t equals 4t plus 10, 4t plus 6, and 4t plus 6. Now, if you'll recall, I mean, you could leave it in either one of these formats, and you would technically be correct. But just a little bit of bonus material on top of this. If we look at the components that we use to build this normal line equation, we used a point and a normal, right? A normal vector. Now, would that work if this normal vector was bigger or smaller? Yeah, it would. I mean, we could do a normal vector that was this size, and it'd still be a vector that was along the line. And we could do a normal vector that's this size and would still be along the line. Right. So that means that if we multiplied uh, n by a scalar, it should still work to give us either one of these equations. Right. So let's say that instead our value is going to be 1, 1, 1, right? We divide by 4. We multiply by 1/4. Now, this vector still has exactly the same direction as this one, so it should work to give us both the plane equation and the normal line equation. What you'll find out is that we ended up, when we were doing the plane equation, we ended up dividing out by 4 if you go back and look at it, which would have been the exact same thing as when we just divided by 4 before we even got started. Now, for the normal line equation, if we use this normal, then these 4's right here, all of these 4's, they all just drop out. And you end up with a much simpler set of, or a much simpler system of equations. And the vector equation here is also simpler. You just have t plus 10, t plus 6, t plus 6, and there you go. All right, now if any of this was confusing to you, any of the plane or line equation portions, please go back and look at my uh, line equations, my plane equation videos, and this should make a lot more sense, and come back to this and watch through it. All right, thank you for watching, and have a good day.